So since this is the last talk of the conference, Ludmil is not here, but he may see the recording, so we can just thank the organizers for a very nice conference. Very interesting for me, at least. I think learned a lot of things. So what I'm going to talk about is something that I've been talking for a while now. So I apologize for those of you who might have seen some of this stuff. I try to, there is something new here, hopefully interesting. So since the audience is not the usual audience of a talk about Schobers or mirror symmetry, I will start with some examples. So let me start with two very simple examples in Toric mirror symmetry. One of them is the an-1 singularity. So basically, this is the singularity xy minus z to the n equals 0. It has a nice toric interpretation. So namely that if you want to think about it in terms of fans, the way to do this is you take these vectors v0, v1, vn, 1, 0, 1, 1, up to 1, 1n, and you consider the fan supported on those vectors. So in terms of the dual picture, the dual cone is what I call the sigma dual there, and then you get exactly as I said, the singularity an-1. So what's interesting about this story is that toric geometry provides sort of combinatorially resolutions of this Gorenstein singularity. When we use the word resolution, we have to be a little careful, namely it has to be thought of in terms of in the world of the Lim-Mumford stacks. These are not basically, they're not that bad in terms of their geometrical meaning. They're just orbifolds essentially. But in that sense, any of the pictures here, including this one, where sort of the fan has only one cone, if you want, is as good as this last one, where you take the full resolution. I guess it's an n-1 chain of p1s. So, and that's kind of an important aspect of this story. When we use the word resolution, we have to do it in this world of the Lim-Mumford stacks. And as far as I'm concerned, the main reason for doing it this way is that if you want to do homological mirror symmetry, life is much better in this world of stacks. So now, continuing with this classical, very classical point of view, this goes back now, I guess, maybe 20 years or so. Of course, the story of mirror symmetry is even older, maybe 30 years now, but this sort of was made explicit in a way in a long paper by Horja and Vafa, where they wrote down exactly how this dictionary should work, namely on the left side, you have birational geometry, where you take birational equivalences. So essentially, what you do, you, as I said, you take different resolutions, which in the world of Deligne-Montfort stacks, as I said, they're all as good as any. And on the right-hand side, what you look at, you look at the mirror, and one way to think about this mirror, the way they phrased it is this is a nonlinear sigma model. So the mirror you can think of as Y as a hypersurface in C star cross C2. So it's essentially, it boils down to taking polynomials with of degree n in one variable, where u and v are some kind of dummy variables in order to obtain a mirror of the right dimension. You may well get rid of them, and then you can write some lambda Gesper model. But here, I put the u and v there. And what the classical story is, you take the moduli space of all these polynomials, essentially, as I said, and there will be a mirror fibration, a Milnor fibration, sorry, and classical discriminant locus. And of course, this is a very classical problem that you then study how the monodromy acts on this Milnor fibration, and you write down periods. So on the left-hand side, though, you have, as I said, the world of the birational world, where you take birational equivalences, and what became apparent then by work of Bondal-Orlov, and then extended it to the stacky world by Kawamata, that this is related to the notion of derived equivalences for the boundary derived category of coherent sheaves. So I haven't written explicitly here. There's something called the K conjecture, but we will not deal explicitly with that here. So the kind of general philosophy here is that underlying all the papers, as far as I can tell, on Schobers. Of course, nobody sort of these days writes explicitly this, but I think as a intuitive picture, this is very useful, is that on the left you have some kind of stringy Kähler moduli space. So one can think of, I think the physicists, when you can write down a metric for this, they do, in fact, and you can think about this as a kind of quantum corrected metric. And this is a huge story here about, of course, how to do that, how to write the Frobenius manifold associated to it. And on the right, the more classical story of moduli spaces of a complex structure, which is sort of more related to the topic of this conference, where you can do Hodge theory and all that. So, what's good about toric geometry is this remark was made by Batarev that in the toric case, you can actually write the periods and their solutions of something that was introduced by Gelfand, Kapranov, Zelebinsky. It's a GKZ hypergeometric system of PDs. So, so in a way, as I said, on the left, we have this space, which to this day, as far as I can tell, has not been defined in general. There are all sorts of approaches to it, including, of course, Bridgeland's space of stability conditions. By the way, these are supposed to be the geometric stability conditions inside Bridgeland space. But anyway, something that is not explicitly defined is supposed to be equivalent with something very classical. So the second example is the famous, at least in these papers by physicists, where they can actually compute things. It's called a two-parameter example. So basically, you take a take this weighted projective space, which has a surface of Z2 singularities, blow up the singularities, get some kind of something which is called X. And then again, if I haven't written here the combinatorics, but if you write down really explicitly the combinatorics, at least from the toric point of view, you have four equivalent, as I said, in this world, they're equivalent resolutions, or the physicists would call them phases. So it's here is the total space of the canonical bundle on this fourfold. So that's going to be what's called the local Calabi-Yau. So it's a fivefold. Here is the total space of the actual weighted projective space, which turns out to be, in fact, a as a singular as a variety, but as I said, we're working in the world of the Riemann for stacks. Then we have this quotient stack. Turns out then in this case it's C5 over Z8. And then also something which looks like a toric bundle. I put it in quotes because it's not quite a bundle in the classical sense, but it is. It comes from this projection that I pictured there. And even for this example, in fact, there are tremendous complications if you want to understand this. If you want to understand this identification of the Kähler space and the complex space. So the Kähler moduli, stringent Kähler moduli space, and the complexes of the mirror. So lots of things are known, but it's still quite challenging. And so the advantage, as far as I'm concerned, of using this PD system is that it allows a very explicit study of the moduli space of complex structure, a global study of the moduli space of complex structures for the mirror. Namely, what you do, you take a polynomial, a Laurent polynomial, based on whose Newton polytope is given by the convex hull of the vectors Vi, which I haven't written, as I said, for this case, but that's a very, very general story. And the periods that you write down, at least formally, they're always this oscillating integrals. So e to the f x to the some beta, there is a parameter beta, and the integrating measure, the usual measure that you have to take when you do some kind of log integration. So I should maybe this is a good point. Sometimes it's quite important here that you have to allow for a parameter which people like to denote by h bar, and I think there were some talks at this conference that mentioned the asymptotics with respect to h bar. So I'm not going to touch upon this, but this is kind of important. And so the picture that one sees here is, in this example, is something like this. So this it's a simplified, obviously, picture. So so this is the region of. So I had these four resolutions. These are kind of at least the regions where the resolutions of right here, these four resolutions correspond to this four regions in the moduli space. And this can be made quite precise in this example. There are the thing to note here, although this is, as I said, even this example is quite complicated. There are two important and non-trivial components of the discriminant locus. So the main one, the principal component, is the sort of classical one. This one is not that classical, but it corresponds to taking a restriction of the polynomial on one of the faces of the this convex hull. So, and I will say more about this. So the picture, the vague picture that the vague conjecture I'm making right now is, and again, this is kind of as far as I'm concerned, underlying all the works that appeared, and there are quite a bit lately in this world of Schobers. Even some of them are not called Schobers, but they don't use that word, is that what the expectation is that there exists a B-type sheaf of categories with stability conditions, where the generic stock is either the, I'm interested here mainly in the derived category of Korean sheaves, but of course this is mirror symmetry. We expect this to, everything I'm saying here, to have a mirror part, where, so the generic stock is, these are called the B branes in physics, is made of the this derived category of coherent sheaf, bounded derived category of coherent sheaves, so that if one moves around in this yet to be defined moduli space and yet to be defined, the yet to be defined Schober will have a property that if you move from in the smooth part, you will get something categorically, which is given by a Fourier-Mukai functor. So this is, by now we can say, a little more classical. It has to do with this Kreppen resolution conjecture and some older work that I've done with Borisov. So now the sort of new, and as far as I'm concerned, aspect of this is that what happens at the discriminant, and the conjecture is that this sheaf of the sheaf of categories has the property that approaching the discriminant locus corresponds to actually taking a spherical functor. So this, what the spherical functor is, I will say a little later, but it's one of these notions that again have appeared in a way naturally in the story when people try to think about mirror symmetry. So so the Fourier-Mukai functor I already mentioned. This is this work of Bondal, Orlov, Kawamata. The spherical functor story goes back to this famous talk by Kontsevich, the paper of Seidel and Thomas. In fact, the ones that show up in this geometric picture are the type that I called easy spherical functors. And this story has been sort of then formalized in a nice way in a series of papers by Ano and Logvinenko. And the conjecture about the spherical, the fact that approaching a discriminant locus corresponds to a spherical functor appears in a physics paper by Aspinwall, Plesser, and Wang. So, and as I said, there should be a mirror picture of this in the Fukaya world. So let me just for, as I said, since the audience might not be familiar with the language of Schober, let me just say one word about how this came about as far as I understand it. So this has been noticed in a paper by Kapranov and Shechtman, namely that there is an analogy between spherical functors and perverse sheaves on, say, a disk with the stratification in the complex plane with the stratification at the origin. The definition of the spherical functor is that if you have two k-linear DG categories, C and D, S is spherical if these two conditions, so S and R are the, L and R, sorry, are the usual, I guess I have one of these is wrong. Let's see, SR, R, so I think SL here, I believe, that these are equivalencies. So the cone of the usual adjunction that you write down, the two cones T and C are equivalencies, and this is kind of, as I said, this was made turned into a general definition by Anoy and Logvinenko in this way, and the way you should think about T and C are the usual monodromy functors that you get, say, in classical geometry. So what Kapranov and Shechtman noticed is that there is a nice result, which I think goes back to maybe work of Malgrange, maybe Maisonneuve, and other people probably, who noticed that if you want to understand the perverse sheaves on the disk, as I said, with stratification given by the origin and the rest, then that's equivalent to giving, so the usual couple of nearby cycle and the vanishing cycle is equivalent to giving a two finite dimensional k vector spaces with the corresponding maps alpha and beta, such that 1 minus beta alpha and 1 minus alpha beta are invertible. In fact, if one of them is invertible, then the other one is too. So, so you know, so if you replace, if you sort of categorify in a smart way this definition, you really notice that indeed you can think about the spherical functor as a categorification of this picture on perverse sheaves. So I should mention that there is now a quite remarkable paper by Kapranov, Soibelman, and Sukhanov, where they push this a little further and they categorify Schobers on actually surfaces in the world of, with a sort of main goal of understanding this in the world of Fukaya or Fukaya-Seidel categories. Donovan has some papers, I think, where he discusses this in the world of that I'm discussing here, mainly of the B brains. So my question here is, what's the analog of this in higher dimensions? And the point of this that I'm trying to make is that we already know something about this perverse sheaf, namely that the period satisfy the GKZ system. So in other words, and we understand combinatorially, in the Toric case at least, the discriminant locus. I mean, understand, when I use the word understand, what I mean is understand what the components are. The topology and all that is still very difficult, but we still have this sort of theory available and the usual regular Riemann-Hilbert correspondence available at our disposal to try to understand this Schober. So, of course, we don't know even what the higher dimensional Schober is right now. We sort of are guessing, we're making guesses. And then, of course, there is, as of now, there is no Riemann-Hilbert correspondence for Schober, although I think probably that will change soon, at least in these examples, one-dimensional examples like Kapranov, Shechtman, and this latest paper by Kapranov and Soibelman and Sukhanov. So let me quickly present the general Toric context. So, you know, you start with a bunch of vectors as we started. This is traditionally called the A set. We have a bunch of vectors, which just for purposes of the theory being nicer than otherwise would be, we assume that they're all included in a hyperplane. So there's this hyperplane condition here. We call delta the convex hull of these vectors. And as before, if we want to talk about resolutions, what we do, we take sigma to be a simplicial fan whose rays are generated by vectors in the VIs and whose support is the cone generated by this polytope. So, and then we call x, we look at the toric stack, and it turns out that this toric stack, in this case, it's going to be the resolution of a Gorenstein singularity, which is given by the spec of the, is basically essentially given by the dual cone. And, you know, we look as we did in the example that I started with, we'll look at this F, that's kind of the classical mirror symmetry, where the projective Calabi-Yau that you talk about, say the quintic, for example, could be an example, would be the proj of CF sigma by this vector F. So both examples that I discussed in the beginning actually do not concern this example of a projective Calabi-Yau. Namely, I'm cheating a little bit here. So instead of looking at the proj, I'm looking at the spec of the cone, just because if we work with periods and the GKZ system, going to the hypersurface involves some kind of yoga, which is, you know, adds a further level of complication to the story. So again, Batarev noticed this fact that the periods can be written as solutions to a D module. And D module, I wrote here a version of this D module that I defined with Borisov, and we believe that, not that we're trying to be diplomatic here, but at least for mirror symmetry, this sort of D module is better behaved in the sense that it is functorial, and the sheaf of solutions has the right dimension. So in Gelfand, Kapranov, Zelevinsky, there was this issue that if the set A that you start with is what's called not normal, then the rank of the sheaf of solutions may jump. And of course, for mirror symmetry, that's a bit of a problem if you're trying to do functorial stuff. So our system is almost the same. It's a little more general, but it cuts down the solution, the rank of the solution set exactly to the right rank. So of course, in the good cases, including in the normal case, it really coincides with the classical GKZ. So you see, this looks like it may be an infinite dimensional. So it consists of an infinite set of functions, phi v, where v is inside this cone. Well, as it turns out, you can cut this down to, of course, a finite dimensional set. So, namely, these the first equation, by the way, should, you know, remind people of something like a differential equation, and there are versions of this that people have studied. So, and again, the main thing about it, as I mentioned, is the fact that it has the right dimension. So a remark in the context of this conference is that the Fourier transform of this system is, in fact, it goes back to the systems that Harishchandra wrote down long time ago, and I think they came up in some of the talks, and they were studied later by Hota and Kashivara. Of course, they were interested from the representation point of view in Lustig. The famous results of Lustig are all concerned with systems, can be understood or can be phrased as systems of associated with some symmetry given by a group G, usually a reductive group, so if you take the Fourier transform of this system, the sheaf of solutions, then it's going to be you'll get solutions as distributions, and that's exactly the context of, as I said, of these Harishchandra results. So in a way, I haven't written anything here about this, but that, of course, opens up the question, and this is something that I really haven't thought about it, but I think there are people thinking about this. What happens for more general groups and more general Grassmannians? So, in fact, there are, I think, some works in regards to that in the context of Landau-Gisburg model. So, one remark here that is that if I take this system is kind of the way defined this way. So that's another advantage of the BBGKZ. So what we call BBGKZ, better behaved GKZ, namely that it allows you to just take systems where the V here, the set of is indexed not just by the whole cone, but by elements in a subset of the cone closed under addition, and that's very useful also in mirror symmetry. So as I said, we're after this trying to understand this identification between the stringy Kähler moduli space and the moduli space of complex structure, and we the solutions essentially the way we're going to think about them are is this big function Z. In the physics language, that's called the central charge. And the crucial technical tool that, as far as I'm concerned, if you want to sort of draw the direct link between the two sides, other than identifying, as we usually do in homological mirror symmetry, we usually, you prove homological mirror symmetry by proving that the derived category of coherent sheaves on some variety is isomorphic with some Fukaya category or Bragg Fukaya or anything Fukaya-Seidel or anything of that sort. But there is the identification is sort of on objects and on morphisms and or on generators. So it's not quite a direct link between the two sides. So the only link I'm aware of is, in fact, this what I called, that's just my terminology, the topological mirror symmetry map, which goes from the Grothendieck group of the toric stack, in fact, from the dual to solutions to this GKZ system. And this is very explicit again, and in this combinatorial language can be made very, very precise, and it allows for the presence of this parameter beta here, which again I'm not going to say much about it, but it plays a role in this story. So so this goes back, of course, to the first proofs of mirror symmetry. And in fact, I think this shows up before the proof of mirror symmetry in papers by Giventhal in his international ICM talk. The other So I want to make a point here, since there are some people here who are not maybe familiar with the mirror symmetry world. So what in a way, the missing point of view here is that we would like to lift this identification, this topological mirror sim, to a categorical map. So in other words, we would really, what it's really missing in order to kind of prove the full homological mirror symmetry this way is to draw a direct link between the hypergeometric functions, or the D module, and the actual derived category. So not K-theory, not just the sheaf of solutions, but really full powered derived categories, and perhaps abstract sheaves of solutions in some way. So I thought about this. I asked people, or thought about this, and I have no idea how this can be phrased or done. So just one word quickly about the technical details of this. So what's this? It's kind of a deformed Grothendieck group. So the beta plays a role of a deformation parameter, and so there is something that I'm suppressing here. So so this group has a very combinatorial definition, namely these R1 RNs correspond to the classes of the equivariant invertible sheaves, or line bundles in the classical case. And there is some condition that if you have sets that do not generate a cone, then you put a condition that 1 minus Ri equals 0, and then some linearity conditions where the beta comes in. And so if the beta is not integer, then this loses this classical point of view. And as I said, there is a story here where you can, in fact, if you move in this, beta is a parameter in the Lie algebra, can be thought of as a parameter in the Lie algebra of the torus. So if you move beta, you're going to hit some walls, which turns out that there are hyperplanes in this case. And but that would be another talk, and be interesting to. In fact, I think I put here the lemma, so that for generic beta, this deformed K group is semi-simple, but the walls are hyperplanes, and I don't know what their interpretation is. I'd be interested to know that. So the solutions one writes down are of this form. So they contain the gamma functions, and oh, I see something. So this should be log of Ri. So you take sort of some log choice. You make some log choices from Ri, and you can think of the Ri's here as kind of operators. So you take their log. There is some ambiguity there, but the ambiguity in choosing these logs, but the ambiguity is fixed by imposing this linearity condition, and then you kind of sum over these, and this is kind of the magic sauce in this story. So that's kind of that gives this connection, as I said. So I was just quickly gonna mention this something which is in fact quite. It has an interpretation in terms of the wave filtration and mixed Hodge theory, but so let me just quickly mention this point of view, because it might be also useful, although I haven't worked this out. So this is due, I think, it's kind of shows up in various places to Edelson, although he didn't publish, and there's a few papers by Mochizuki who uses this quite a bit. So the point is that this BBGKZ that we wrote down can be interpreted as a twisted de Rham complex. or some people call this, I think nowadays it's called a dwarf crystal. So what you do, you sort of create a generalized log twisted de Rham complex. So log, as you see, these are log forms here, and twisted because there is a this beta plays a crucial role here. And what Adelson showed is that in this case, in this particular, so there are various versions of this of Dor crystals that one can consider here. So this is one. The version I'm writing is one. You can, depending on what kind of vectors, what properties the sets are, you're going to get other properties of this complex. But in this case, the only non-vanishing cohomology is in the maximal degree I equals n, and in that case, this module is going to be R over this ideal, and the ideal again is defined by these twisted operators, and the connection with the D module is that this in fact can be enhanced, and this, as I said, it's quite crucial in this story of crystals, to left D modules, and then one can show that in that sense the solutions to this W beta, which now is viewed as a D module, is exactly the space of solutions to this BBGKZ. So, and so the question about understanding the discriminant and all that can be phrased, in fact, can be phrased in terms of this Dor crystal. So, so again, it's algebraically is a very natural notion. So, okay, so let me now move to the more categorical part. So, what's the so the non-classical, if you want, story here? So what what Gelfand, Kapranov, Zelevinsky have done in their book essentially is that they shown that for such a configuration as earlier as before, if I have the set A set again with a hyperplane condition, they build this gadget, which I think it's called the A determinant. So it's, instead of taking the classical discriminant for the whole set, you take a product of the classical discriminants corresponding to the intersections of the given set with the faces of the convex hull. So you will have one discriminant component, well, one term here for each face of the convex hull. There is some multiplicity, which has to do with the properties of that face, and some of these, as it turns out, some of these are components. Some of these factors are going to be trivial, and that corresponds to the cases when this A intersected gamma is a base of the a subbase, if you want, of the lattice. So if that's the case, then in a way this component is trivial. But in the cases when this is not the case, then you'll get the true term. So 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 what is important for us here is that this A determinant gives on the nose, at least in the case of the BBGKZ, or in the normal GKZ case, normal set A for the GKZ case, the characteristic cycle together with the multiplicities of the D module that we're studying. So in a way, we have an algebraic shortcut for understanding these components. So what, as I said, the way this was phrased in this paper by Aspinall, Plesser, and Wang was that for each face gamma in each triangulation, so in other words, each dilemma for stack structure on the underlying X sigma, there is a spherical functor of the form dB z of gamma with values in which lands in dB of X sigma. So the z of gamma is something that is defined. So the X sigma is the usual dilemma for stack, as I said, and Z gamma is the toric stack determined by the cones that are in the star of this face. So this is in a way, again, a very combinatorial structure, very combinatorial construction. So what's remarkable about this is that so it may seem that this is too simplistic, and maybe it is, since we have to deal with some multiplicity. But what's remarkable is that while this category is given, it may be, in fact, that the actual functor here changes. So while moving along the discriminant locus will make this sort of spherical functor change, in the sense that the image here may change inside. And this kind of one can see in some example. So as I mentioned, the multiplicity that shows up in the formula, and it has to do with the multiplicity of the component in the characteristic cycle, has to do with torsion. And in fact, as in the world of toric stacks, torsion, although a little bit unpleasant, it's manageable. Toric dilemma for stacks, sorry. The torsion is understood. And in other words, instead of working with the lattice, you work with finally generated abelian group. That's one thing. And the other observation is that the BBGKZ itself is defined, that we defined, is actually defined exactly to capture the torsion case. So we do not have to start with n a lattice, but we can start with n being, as again, a finitely generated abelian group. So the picture that we're going to see is that we have Z gamma, as I said. E gamma is kind of the exceptional locus, and it's embedded in the ambient toric dilemma for stack, and the spherical functor that we expect to be is the composition of the natural composition of these two functors. So so the remark is that we expect to get such a spherical functor for each stratum in the Whitney stratification of the characteristic cycle. And so then in this, as I said, the point is to understand the B-brain category. And what we do, we take we do a Cyto localization. So this has been, again, worked out by Cyto and used extensively in mirror symmetry, in fact. Usually it's done on the Fukaya side or the Fukaya Cyto side. So we take a natural transformation from the identity, which is from the identity to the spherical functor, and we do a localization. So the two extreme cases are then when this gamma is a vertex, and that corresponds to d gamma being a divisor, and then the associated spherical functor is going to be simply the tensoring by the O of d gamma, so the tensoring by the line bundle, and then the B brain category is going to be the category of the complement of this divisor. Or then the other extreme is when the face is the full polytope. And then this is the famous spherical functor where Z is a point and the image is a spherical object. In the case of X projective, this spherical object turns out to be exactly the structure sheaf. So this is kind of the situation described by and studied by Cyto and Thomas. And so I should mention now that there are various, for this Toric case even, there are various papers now available by, some is by Donovan Wemis, a more recent one by Spenko and van den Berg, Zhu and Huang Zhu, and all of them concern that what they call the quasi-symmetry case, where the discriminant essentially it boils down to the discriminant being bunch of hyperplanes, which makes, of course, everything a little easier. So I have maybe, as I said, I want to finish a little early. So I want to just present my take on this point of this quasi-symmetric case. I think I mentioned this before, but let me just go and in this, as I said, new context of people writing down and discussing this quasi-symmetric case, let me present my take on it. So basically, it boils down to what I call the Lorentz construction. So in other words, I start with an arbitrary set A, but I want to produce one using the Lorentz construction, which is, so this is a classical thing in matrix theory, which I'm not an expert on, but I became aware that this is something people do in matrix theory. So you want to study A, but it's easier to study A if you lift it in a way to something called LA. So you're going to have, if you start with n vectors, you're going to have two n vectors. And the magic about this LA is that it captures all the combinatorics of A, namely LA, the Lorentz of A will be, the convex hull of this thing will have all its faces will be determined by points in the set. So while A, if you take the convex hull of A and you want to study the convexity properties may have points which sit inside, LA will have the somehow magically, by basically it's sort of expanding it so that all its faces are produced by points in the set LA. And of course, there is some kind of combinatorial dictionary in terms of matrix, something with bases that make that very explicit. So I call this the Lorentz polytope associated to A. So in a way, LA is the one that is the quasi-symmetric case. So that's what these people have done. And one can prove that the rank of the Toric variety defined by LA is, of course, the normalized volume of the convex hull of LA, but more than that, it's actually the volume of the, it's not going to be the volume of the convex hull of these vectors, but it's going to be the volume of the zonotope determined by these vectors V1, Vn. And this is one of the essential aspects of the work of this work by Spenko and van den Berg, and their Schober is exactly the appearance of these zonotopes. So, and this is another good thing about these Lorentz varieties is that the categories admit a universal tilting generator, so which these days are called non-canonical, non-commutative resolutions. And so there is, again, a very explicit combinatorial gadget that tells you which line bundles you take here so that you get the full collection. So you don't go overboard and you don't undercount, so to speak. So, and again, it has something to do with the gate dual. And now the categories of the dB of Z gamma that show up in the definitions of these spherical functors also admit tilting generators. So this, the spherical functors in this case are very explicit and compatible with topological mirror map. So the point about these about this Lorentz construction would be, can we go backwards? In other words, we start now with the quasi-symmetric variety, the Lorentz variety. Can we go back to the general Toric case? And this is not easy, but I think I can say something in certain cases. And this would be quite something. Will go a long way towards understanding, as I said, the general Schober that is required here. But another point, and even more importantly, maybe, that, as I mentioned, this taking the Fourier transform of this GKZD module takes you to the world of distributions and hyperfunctions. And as far as, so the hyperfunctions are, in a way, precursors of the theory of microfunctions that people have been using in mirror symmetry. And the question is, and they seem to be very amenable to the analog in categorical theory of taking semi-orthogonal decompositions. And in fact, in these works by Donovan especially, and this more recent one that I mentioned by Soibelman, Kapranov, Soibelman, and I forget the name, Sukhanov, I think, that this is the point of view they're taking. So they sort of do not do localization, but they built the semi-orthogonal decomposition. So and it seems that this is, as I said, something that is compatible with considering here generalized solutions, hyperfunctions, as it was done in the old days by Kashiwara in particular. So, okay, so I will stop here. Thank you for listening.
All right. Let's thank Paul. Questions?
Well, Ludmil, since you're not here, but since this is the last talk, we want to thank you, and I want to thank you for.
Sorry, I mean the connection was lost.
So one more great conference. So please, everybody, let's thank Ludmil again for organizing a great conference.
So there will be one small event in December, and then we'll proceed in January. So thanks everyone for participating, and have all of you happy Thanksgiving and happy holidays after that. Stay safe.
Thank you, Ludmil.